Hey guys, what's going on? This is the first video in a while, and I did round 696. As you can see by my standings and all the wrong submissions I had, this was quite a bit of a struggle. But, you know, I guess that's how it goes. Other people have also had some issues. I'm not exactly sure what happened with me. Maybe I just had the wrong idea, so I guess I will confirm this later on C. But anyway, I don't usually do plugs here, but I think this channel is like drastically underrated. So this guy whose name I'm not going to try to pronounce basically makes both text and both text editorials and screencasts. And I think he deserves more attention for what he does. So you guys should at the very least give him a shot. But that's up to you. And anyway, enough YouTube stuff. Although you might want to subscribe to my channel too, wink. Yeah, okay. So we're here for solutions, and that's what I'm going to do. I don't know if my E is correct. In fact, I kind of want to look at someone else's and see what they did. Beta insert IT. That. Okay, that's like almost exactly what I did. So I must have screwed up implementation somewhere. In fact, can I see the test I got wrong? I probably can't, but... Okay, whatever. I'll share my idea and then try to debug it later. Alright, so here is the plan. Just going to go over solutions briefly. Don't exactly have that much time, but yeah. Oh, and by the way, I'll link the guy's channel in the description. Yeah, okay. So for A, we basically have a binary string of zeros and ones. For example, let's take 0, 0, 1, 0, 1, 1. And let's go. So basically what we're going to do is we're going to take some other string and we're going to add the other string to it like bitwise, sort of. So if I do this with this, the resultant string is going to be 1, 0, 1 plus 1, 2, 1, 1, 1. And then we compress the string so that equal characters get mashed together, kind of. So like this would become 1, 0, 2, 1. And what we want to do is we want to pick out this red string that maximizes the value of the orange string. Or, sorry, the resultant string, the compressed one. And so the first thing is that we have numbers. So having more digits is always going to be better. And therefore, we want to make it so all the digits are not equal to their adjacent ones. So for example, let's take this sample. I will draw it out once again, 0, 0, 1, 0, 1, 1. And well, we want to make it have as many digits as possible. We also want to make it as large as possible. And it turns out we can do both at the same time by using greedy, or with a greedy strategy. So first we make this as large as possible. And we say, so this will become a 1 because we want it to be big. Then we make this as large as possible while not making it the same as the previous one. Because to make every character unique and not like not equal to its adjacent ones, we just need to make it like not equal to its adjacent ones, which is sort of by definition. So if we do this, then we can't make this a 1, so the best we can do is make this a 0. And then here, we can make this a 1 or a 2. It doesn't matter because either way it's not going to interfere with this one, so we can make this a 2. Here we can make this a 0 or 1. We want to increase it, so we make it a 1. Here we can make this a 1 or a 2. We want to increase it, so we make it a 2. And here we make it a 1. Now this works because A, doing greedy is the best we can do because we always want to maximize the earliest possible values because each earlier digit has more weight. So much weight that it will completely outweigh any decision we make in the future. So we always want to do best in the beginning. And using this strategy, we can also always make it so the digits are not the same. Because, well, let's say we can sort of just do out the cases, right? Let's say we have 0, 1, and 2 on the previous value. Then if we have a 0 here, if this is a 0, we just raise it to 1, and then it won't be equal. And if this is a 1 already, then we're good. And if this previous value is a 1, then if we have a 0, we don't raise it. If we have a 1, we do raise it. And if we have the previous value as a 2, we just don't raise it. And we can do the same casework for it in the future and show that we'll never be forced to have a collision. So that's basically the idea. Do greedy and just take as big of a string as possible. And I sort of messed up my own notation here, but that's fine. Problem statement has recently been changed. Okay, whatever. So for B, we're given a number D, and we want to find a number A such that for all the divisors of A, where a divisor is just a number that divides A, or that A is divisible by. So like say the divisors are 1, 4, 7, and 28. Then we want to make it so the gap between all of the divisors is at least D, and that A is smallest possible, I believe. Yeah, and that it has at least 4 divisors. Okay, so if we give it more than 4 divisors, then we can like sort of take out some of the divisors and just be happy. So we can assume that we only have exactly 4 divisors. And now we sort of pull upon we pull upon a bit of number theory here. If we have A be the product of 2 primes, B and C, then the divisors will be 1, B, C, and B times C. All of which are unique, all of which clearly divide A, and nothing else divides A because, well, it's just these 2 primes. By definition, these primes have nothing else that divide them. And we can show, it's like clear that the best way to represent A is the product of 2 primes, because if we have any more primes, or we have like C squared or something, it's going to be unnecessary. We already have 4 divisors. There's no reason to make A bigger, because it's just going to make it harder to satisfy this condition as well. So we only want 2 primes. If we have anything other than 2 primes, it's going to be more than 2 primes, so it's going to like screw up our prime decomposition, and let's not do that. So we basically just want to pick 2 primes such that these divisors are far enough apart. And okay, so we know we kind of don't have to worry about this gap, the gap between B times C and whatever the biggest prime is. Because if we have like B times C minus max B, C, because that'll be the gap we get between this. Then it'll be like, assume B is greater than C without loss of generality or whatever. Then we have B times C minus B. So we have B times C minus 1 is the size of our gap. Right? But like, we already need this to be greater than or equal to D, which means that we also know that, and actually it's going to be 1 is less than or equal to C is less than or equal to B is less than or equal to B times C. So basically we know that C minus 1 will be at least D, which means C minus 1 is positive. And we know that B minus 1, so B minus 1 is greater than C minus 1, which is greater than or equal to D minus 1. Actually, no, which is greater than or equal to D. And this is this just kind of gives it away, actually, because this is the difference we get. So both of these numbers are going to be greater than D, meaning that like no matter what, we don't have to worry about this gap. It's just going to be bigger. So basically all I'm showing is that we only really care about 2 things, the gap between C and B and the gap between 1 and the minimum of the 2. So we really just need 2 primes such that, assuming B is greater than C again, we need 2 primes where C minus 1 is greater than or equal to D, and B minus C is greater than or equal to D. That minimizes the product B times C. And so now, like, all we really need to do is just pick the 2 smallest primes we can. Because say we, like, Yeah, we just want to pick the two smallest primes, because if we have any larger ones, then there's no point in doing that, because we can sort of like shift the primes downward. And specifically, we want c to be equal to 2. Because if c is greater than 2, then it also means that b is going to have to be larger, because we're going to have to shift it more to the right to satisfy the condition. Meaning that if we make c greater than 2, both b and c are going to be bigger. So that's bad. So we might as well have c equals 2. And then we just pick b to be the largest prime that's at least distance d away from 2. Just pick like just pick the smallest b that's greater than or equal to 2 plus d. Actually, wait, do we want it to be 2? No, okay. I made this mistake in the contest, actually. That's wrong. We want c to be the smallest prime that doesn't break this condition, because I just totally ignored this for a while. That we want c to be greater than or equal to d plus 1. I can't draw at all. C is greater than or equal to d plus 1, and then b is greater than or equal to d plus c. Right. So we pick the smallest c first, and then the smallest b, and then print the answer as the product of those two. Okay, and I'm pretty sure that's what I submitted, so hopefully we're good. Right. Now for C, which I did not get, there were some problems. I didn't fail system test, right? Okay. There were some problems indeed, where I had fun. That's what matters. I had fun with this problem. The TLE was stupid. Ignore that. That was me making a stupid mistake. But okay. This is the point where the problem statements get complex, so I will assume you've read the problems beforehand. Right. So the basic observation, or so I think, is that no matter what you do, you're going to have to use the maximum element. Because say we have this maximum n, m, and then all of the other values, ai, are less than m, or less than or equal to. So if we don't include m, so we have two values like b and c, both of which are less than m, then we're going to set x equal to the maximum of b and c, which is once again less than m. And no matter what we do in the future, we'll never be able to include m again, meaning that we'll never be able to have m be in an operation, because we already know the current value of x is already less than m, and x is going to decrease at every point, meaning that at every operation we have to include the maximum, or so I think. I'm gonna cast the shadow of doubt on everything I say and try and think about it yourself, I guess, because I really don't know what's going on. I'm guessing it's an implementation error, because looking at Anton's code, it's like basically the same thing, but I don't know. I'm not really sure. So basically the idea is, now that we know that we want the maximum element to exist, let's reverse sort the array. So let's take the sample 3, 2, actually no, let's take a better sample. So we have like 5, 4, 3, 2, 1, 1. I believe that's good. Yeah. So now that we know that we have to include the maximum element, let's we can make x whatever we want in the beginning, meaning that we can make x the sum of 5 and any other element. So we can just try all elements. So let's say, for example, we try 3. So then we have x equals 8. All right, now. So we have initial x equals 8. Then we remove 5 and 3. Meaning that we get rid of these. And then now we set x to the maximum of those, which is 5. Right? But now we know what x is. And we also know that we still have to include the maximum element by the same observation. So we need 4 and some element that when summed with 4 makes 5. Meaning that we need 4 and 5 minus 1. No, 5 minus 4. What am I saying? What the hell? What was that? Okay. Writing tablet being weird. So we need 4 and 5 minus 4, right? But the point is that this is completely predetermined because we already chose what x is. So once we choose an initial value of x, the entire rest of the operations will be completely determined by our initial choice, meaning that there's only one choice we have to make, the initial value of x. So if we can simulate testing a value of x in O of like less than n squared time, then we'll be good. Or maybe better notation is less than O of n squared. So that's all we need to do. We just need to test simulating an operation in a small amount of time. And the easiest way we can do that is to just like, instead of searching through the array each time for a value, we can just store the indices of every value and then remove them as we come across them. And I don't know, I guess that's where I screwed up. I don't know what happened. So yeah, that's how you would do C, I guess. So if you do this in O of n or O of n log n, then you get O of n initial choices for x times O of whatever it takes to try out the values. So you get like O of n squared times something. And the constraints are rather light, so it probably works. Yeah. So that's how you do C. Alright, onto the problems that I did solve, hopefully. These wrong answers are scaring me whenever I look at system test. Okay. Now this one I misread, which made for an even more fun contest, because like, note to self, read the bold. This is an important part. I can't use my mouse. This is an important part. That the piles you swap have to be neighboring, because if not, I have no idea how to solve this, and that's what I was trying to do for like 20 minutes. So yeah, that was fun, because with this constraint, it becomes so much easier. All right, so I'm going to again assume you've read the problem, and now we want a better condition than like, is it possible to do this? We want some sort of like concrete mathematical definition of being able to do this operation. And one thing we can say is, let's do some sort of greedy. Let's take the fourth sample, except I'm going to divide all values by 100 because that's pointless. 21, 19, 16, 30, and 16. Yeah. Now notice this like value on the left. We have to do operations with this left one. And note that we can only make values decreasing, which means if this value is too small, then there's nothing we can do for this left one, because the only thing we can decrease it with is this value. So we might as well say, let's get rid of this value first. And if we can't, then it's impossible anyway. So we subtract 19 from each of these. And then we get, and actually what I did was I did this with the, I did this starting from the right instead, because I sort of found the implementation nicer. So we basically say we're going to decrease from this one first. And again, if you got here, it would be impossible. You'd have this floating 2, and it'd be impossible to get rid of it. So say we do this, then we get 2 new elements, 14 and 0. And now this is 0, so we can just sort of get rid of it. And now we have this smaller array of size 4, which we do the same thing to. Now we decrease 14 from these. And we say that we have 2 and 0. Cross off the 0. Now we decrease 2 from each of these. And we get 17 and 0. And clearly, like, we just can't do anything with this. We're going to be left with this 4, and there's nothing we can do about it. Sort of like long division in a way, but like subtraction. So that is what long division is. I don't know. Parallels. Interesting. Right. So this is the process we can do. This is what we're going to do anyway to check if we have an answer, right? And obviously we can't just like do this because it's n squared and we can't do n squared. What we can do is figure out what we actually require. We're assuming we're going to sweep from the right to the left. And basically what we need is at every point, we need the value that's like on the rightmost to be less than or equal to the value to the left of it. So like for example, we need 16 to be less than or equal to 30, which is true. Then this will come out to 14. Then we need 16 to be less than, or 14 to be, or 16 to be greater than or equal to 14, which is true. Then this comes out to 2. Then we need 19 to be greater than or equal to 2, which is true. And then this comes out to 17. And the special case is that we need the final value to be exactly equal. Otherwise, there's nothing we can do. So what if we tried to compute these values? What if we tried to compute the values that we would get sort of efficiently? So let's say, for example, we have, let's just generalize it. We have A1. Oh my god, stop. I'm clicking some button on the pen and it's screwing things up. So A1, A2, A3, A4, A5. Right? So obviously A5 is A5. And now we have A4 is itself initially and then minus whatever we get here, because that's what we're going to do in the operations anyway. If we ever get a negative value, we can assume that it's impossible. So A4 is equal to A4 minus A5. And then A3 becomes A3 minus whatever we get here, which is this value. So we get A3 minus A4 minus A5, which is A3 minus A4 plus A5. We continue. A2 is equal to A2 minus A3 minus A4 plus A5, which comes out to A2 minus A3 plus A4, and we see that it's alternating. And if we continue to A1, now I got all this while still working with my misread version of the problem. So from here I had no idea what to do for like 20 minutes. I'm not actually sure if this led me to overcomplicate the solution, but this was what I had in mind. Maybe there's something easier, but like who knows, man. Right. So first of all, we need all values to be positive. Otherwise, like say this was like 35 or something, then this would be -5. Meaning that if we have some value being negative, then that means that this value is too big, because it means that we were required to subtract more from here than we were able to. So that means all negative values are like impossible. So if any of these values are negative, it's not good. So we require that all AI are greater than or equal to 0. And also we need this value to be 0, because otherwise it will be something other than 0, and then we won't have finished, because we won't have made the array 0. So we need A1 equal to 0. And those are basically the constraints. So in the initial array, we can compute these values directly and then just like, check this. But we also need to take into account that we can make a swap somehow. And now we ask, what does doing a swap do to these values? So let's say, for example, we swap A3 and A4. Because we go right to left, it doesn't affect anything to the right, meaning we can like ignore everything here. But it does affect things to the left in different ways. A trick we can do often when swapping elements is we can treat them separately. Like, because this will become 30 and this will become 16, we can say that we sort of like, we just add 14 to here and then subtract 14 from here. And then we treat both of these like individual element updates. And then now we don't have a swap, we just have a point update. And yeah. So when we do that, now we need to make it so, how do we handle a point update? Well, let's consider again the alternating nature of these values. And in fact, I'm going to move this down a bit. Let's consider the alternating nature of these values again. And in fact, let's just think about A4 for now. So this value A4 is going to have a positive relationship with A4. This is going to have a negative one because it's alternating. So A3 relies on A4 negatively. Then this is going to have a positive one. It's going to rely on the positive side of A4. And then this one's going to be negative, and so on. We continue. So basically, every value at a different parity of index. So like if A4 is even, then every value at an odd index will be subtracted, will have like the new update subtracted. Meaning that this will change by minus and negative 14, and this will change by minus negative 14. And A4, the ones that increase by the value of A4 will change by positive negative 14. Yeah. Positive negative 14 and also positive negative 14. I just realized I totally overcomplicated this, but whatever. Right, so we know that we affect some prefix of the array on even indices by some value, and we affect some prefix of the array on odd indices by some value. So we really just need to check, after making this update, do we have the conditions satisfied? And the way we can do this is by treating even and odd indices separately. For example, what I did was I built a segment tree on the even values and the odd values and treated this like a range update. And then to check if any value of AI is less than 0, meaning the condition is not satisfied, you can say that the minimum, the global minimum, must be less than 0, because that means there's some value less than 0. And if the minimum is greater than or equal to 0, then every value is greater than or equal to the minimum, meaning it's greater than or equal to 0. And then, of course, we can just check directly if A1 is equal to 0 or not. So you can do this however you want. Again, with a segment tree, like some array of prefix maximums and stuff. Really, whatever you do, it's probably going to work. And then just check at every query and check at every point if it's possible or not. And then be sure to undo the swap afterwards, because you can only make one swap at most. So this was sort of what I did for my own segment tree. I made it so this was like A1, and then infinity, and then A3, and then infinity, and then A5. And then this would be infinity and A2, and then infinity and A4, and then infinity. And that way you don't really have to worry about even and odd indexing. You can sort of like apply the range update to here. Say this would be like minus 14. I'll show you. It would be here. This would be minus 14. Again, applying it to A4. And then this would be plus 14. And of course, infinity isn't changed. And since we want the minimum, we really don't care about the infinities. So it's sort of like an implementation trick where we just get rid of a bit of messy indexing. But yeah, that is what I did basically. I was behind this. I was doing pretty well in the beginning of the contest. I was like 20th on A and B, and they just totally fell behind after not getting C at the very least. Okay, this is not easy. Still getting used to this writing tablet. I think I'm getting better at it now, but I'm still getting used to it. Okay. So that's D. That leaves E. See if I fail system tests. Okay, so we got D. How many pretests did E have? I guess quite a few. So maybe we'll test. Kind of scared. I'm not sure if my solution's right, actually. Although I don't know how you'd be able to do better. So I did kind of clutch this one a bit with 5 minutes left. And then C was kind of a struggle. Okay, anyway, I'll explain the idea I have, and if it ends up being wrong, whatever. So I'll assume you read the problem again. Actually, this problem is kind of weird, so I will explain the statement. Basically, assume you have some permutation, like 2, 3, and 1. And basically what you can do is, in one operation, you can pick some value. Actually, wait, is that how that works? No. You can pick some index where, your goal is to make it the identity permutation. So you have an initial permutation, you want to turn into the identity permutation. And all that means is that every value is equal to its index, if we want index. So what you can do is, in one operation, we can pick some index and then send the value to that index. So if we pick the index 2, then we can pick the other index that has 2 and send the 2 over to its correct index. I don't know what the point of this problem was, actually. It's sort of just like making the right assumptions. So we can send 2 over to its right index. Okay, now the cost of doing this is the distance between the indices squared, which means if this is index I and this is index j, then we have j minus I squared. Now, we have a robot doing these operations, and this robot's sort of evil. So this robot is trying to maximize the cost that it takes to do these operations. Meaning that for any permutation, the robot will do it in a way that maximizes the sum of these costs. And I'm sort of messing with the statement a bit, but we can assume the robot is even more evil, and it's going to choose the permutation that maximizes the worst case possible cost of that permutation. So you want the permutation that like produces the highest possible cost in the worst case over all permutations. So it's like the worst case permutation of the worst case cost. That's the idea of what it is. Right. And so what we have to do is we have to print the cost. We have to do everything basically. We have to print the cost. We have to print the permutation. We have to and then we have to print the operations we actually do, like the sending of the values. Now, the initial trap to fall into, which I did myself because I'm not smart, is this permutation. We have 2, 3, 4, 5, etc., up until 1. And the idea is we make every gap as large as possible, right? So we send 1 to its correct position, meaning that we have now 1 and then 3, 4, 5, and 2. Then we send 2 to its correct position. And we have 1, 2, 4, 5, 3, and etc. And the point is that it always makes the largest jump possible, right? Okay, so I got E. Cool. And that's the idea. But it's the wrong idea. Because so this gives us a cost of the sum from I equals 0 to n minus 1 of I squared, which turns out to not be that good. We have, for example, like 16 to like 30 for 5, and for 4 we get 14, which is not optimal, because we can do something better than this. And I don't know how to prove that the better thing is optimal, but it works. Proof by AC, you know. So I have nothing more to say. Maybe there's a proof for this. I just don't know it. Actually, I think there is a quite simple way to prove it. Basically, what we're going to do is consider like the final 2 indices. Right? Both of these cannot be involved in huge jumps at the same time. Like, for example, say we have 5 ... and then 1. Both of these can't be involved in the largest jump, because if they were, that just like wouldn't exist. How would that be possible? Because doing this, note that every operation will correct at least one element, meaning that every operation leaves us with like at least one less out of place element that we can use to manipulate. Okay, meaning that there's no way we can ever have the largest gap used twice. But what we're going to try to do, and this is the inspiration for this strategy, I guess, is to make it so every other element takes the largest jump possible, which means either the largest jump to the left or the largest jump to the right. If it's in the middle, we don't care. Which means that essentially, say we have a permutation of length 7 as an example. We're going to make this one take the largest jump possible over here. And this one is also going to take the largest jump possible over here, and this one will also assume is going over here. Then this one is going to take the largest jump possible to the left, and so will this one. And then finally, we'll make this possible. And this is optimal by the definition of the like construction, that we give every element the largest possible jump it could ever be involved in before it gets corrected. And that's the basic idea. And the reason this counters the other argument of like shrinking the permutation every time is that like we do shrink the permutation, but we shrink it weirdly. Like we don't convert an array of n elements to n minus 1. We kick out an element in the middle, meaning that we still have some large gaps that are possible. So that's the basic idea. We pick some split point in the middle of the array. We say that everything except for the first element to the left of this split point will go to this final element. And everything to the right of the split point, why am I using the wrong colors? That doesn't make sense. And then everything to the right of this split point will go to this left point. And then finally, in the end, we do one jump between the biggest ones. Again, this is optimal because every element is involved in the largest jump it could possibly be in, except for the last one because we can't use that at all. So let's do that out of colors. So basically the idea is we have this gap of 3 elements. So we have 3 things to put down here. We have this gap of 2 elements, so we have 2 things to put down here. We have one here, and we have one here. Right. So in the end, we want to have a 1 here after we're finished with all of this. And in the end, we want to have a 7 here after we're finished with all this. So how do we do that? Well, clearly 1 has to be somewhere here. Because if not, then like what? We can't do anything because we need the 1. We're going to involve this index with only these, meaning that if the 1's going to be here in the end, we need the 1 to be here. Okay. And now how did I do this actually? I kind of forgot how this works. Right. So now we need to pick the right element that we're going to send here. Which I think it shouldn't be this. Using my own output as inspiration now. I forgot how this construction works. Wait, it is that. Oh, right, okay. Right, okay. So we can do it either way. We can say that this is 1. And now we need the previous element that we used to be 2. We're sort of constructing it like backwards. This is going to be the last thing we do before sending the 1 to here. Then before we get the 1 here, somehow we need to send whatever's here to 2, meaning that this element has to be 2 before we can get the 1. So we can, for example, put the 2 here. And then now again, we need the 3 to be here before we do that, so we can put the 3 here. And then now this element is 4, so we need to have this be 4, so we can initiate by sending the 4 to its correct location. Then we get the 3, and then we send the 3 to its correct location. Then we get the 2, and we send the 2 to its correct location, and then we get the 1. And we do the same sort of strategy for the right side, where we start with this being something like 5, and we want to end up with 7. So we can do something like this, and then we can do something like this, and keep going backwards, and keep going backwards. So again, this 5 will be sent to its correct location, then we get a 6, then we send the 6 to its correct location, and we keep going. And then eventually we just do these operations in the order that we sort of determine them. We do this first, then this, then this, and then we can do the other side. We do this, and then this. And then finally, once we're done, we have a 7 here and a 1 here. So we do the final largest operation, and the permutation is identity. So that's the idea for E. I guess that's all I have. Yeah, I'm not really sure what else to do. I guess that's E. I didn't even read F because I was busy trying to solve C, but that's fine because there were 2 people that solved this, and they were both after the contest, so that's not happening. Like everyone tried this, even Neil tried it and didn't solve it. So I guess that does it. 134th. All right. With C, we would have been better for sure. Having a score similar to this, except like less bad, maybe. Also, maybe not misreading D would be a good idea next time. So we'll see about that. Other people get wrong answer too. Yeah, a lot of people with that, including myself. Of course, if it was just the identity permutation, but like with a cyclic shift, it couldn't have been that easy. So that would be too hard. Or, I mean, that would be too easy for a div2e, so they couldn't give that in good conscience. But anyway, yeah. I have nothing more to say. You should check out this guy's channel. Again, I think it deserves more attention since there's a lot of effort that goes into it. Does a variety of things, and like including some mashups and cool things like that. So yeah, that's basically all I have. A to E, no F. Kind of disappointed in C, but I guess I'll figure that out later. All right, that does it. Goodbye.